Okay, so here it is, Tuesday the 10th, and this is video 25. We're getting way up there. And it's the second half of 16.2. I probably could have pushed through the first half, but I was having all those issues with internet and videos, and so I don't mind going slow, and so here we are. This is going to be pretty short, and then 16.3 is a big section, and 16.4 is the crux of the course. So we're still working with these vector fields, and we've talked about flow and circulation and work, and now we're going to talk about flux. Okay, so start off with a definition. A curve in the xy plane is simple if it doesn't cross itself. Okay, so here's an example of a simple curve. See? And this guy is not simple because it crosses itself. All right, so to find the rate at which a fluid is entering or leaving a region enclosed by a simple curve, C is the line integral over C of the field dotted with the unit normal, not the unit tangent. So the tangent before gave us direction along a curve and made sense because you're looking at work, but now we're looking at something flowing over this simple curve, and the rate at which it's going in or coming out depends on something orthogonal to the curve, right? Because a unit normal here. Where is that thing? There we go. Unit normal is going to stick out like this, right? Okay. And n is always pointing outward. Okay. And so this is how you measure flux. And it's the integral over C of f dot n ds. And the direction in which we travel around the curve is important. In fact, it's really bothersome, but here we go. Let me get black again here. Why isn't this thing showing up? Here we go. Okay, black. Okay. So let's build some axes here. And let's put a curve here in the xy plane, just a nice simple curve. And let's say we're going around this curve clockwise. Well, in the clockwise direction, what does t look like? T looks like this. The vector k is always sticking straight up. And so by the right-hand rule, with n sticking out here, n is equal to k cross t. Okay, and n sticks out. So if you have the same setup, only now we're going counterclockwise. Get some color in here. T is going to go this way. K always sticks up, and n sticks out, and so now n equals t cross k. Right? So it's important to stipulate which way you're traversing around this simple curve as you're computing the flux, because it changes your answer by a negative, really. So okay, so let's unravel this and get formula for our line integral. So let's look at counterclockwise first. And here n is equal to t cross k. Okay, and that's equal to t is what? Dx dsi plus dy dsj dotted with k which is something's wrong here in my notes. Oh, it's because it's a cross product. Sorry about that. I had a little brain moment there. It's not a dot product. It's a cross product. Okay, so this becomes, oops. This becomes the matrix I, J, K. And T is dx, ds. And this is dy, ds 0. And this is 0, 0, 1. Keep forgetting I have this new pencil app here. Okay, so this becomes I times 2I ds 0, 0, 1 minus J zero, zero, 1 plus K times which becomes dy dsi minus dx ds j. Okay, so this is n in this setup. All right, so now we have, so we're given that f is what, mi plus nj, because we're just working in the xy plane. So then we have f dot n ds equals, so when you dot these, you get m sub xy times dy ds minus n sub xy ds dx ds around c. Okay. And we did this before. This becomes m dy minus n dx. And now we add this cool new thing to our repertoire of integration. And this was the, let me get this right, counterclockwise. So this integral goes around the curve in the counterclockwise direction. So you put a little arrow on there. So it's an O-int is what we say in LaTeX, right? And yes, if you're going clockwise, I think it would be n dx minus m dy, and you'd have the arrows going the other way. So this is counter clockwise rotation. Okay. All right, so let's do an example here. Compute the flux. Let me get, this is an old example. So the example, compute the flux in the field F, which equals x minus yi plus xj across the unit circle traversed counterclockwise. Okay. Counterclockwise. All right. So what do we need? We need the unit circle going counterclockwise. This is the way we always did it in trigonometry. And t runs from 0 to 2 pi. Okay. All right, so we know that flux equals m dy minus n dx. Right. Okay, so what's m? M is x minus y. What's n? N is x. And so when you plug in the curve, x minus y is cosine t minus sine t. And n equals x, which is cosine t. Now for the fun part. What's dy? What is dy? So dy dt is the derivative of sine, which is cosine. And what's dx dt? Dx dt is minus sine t, right? So this is scratch work over here. Okay. So m dy turns out to be, so t goes from 0 to 2 pi. M is cosine t minus sine t. And dy is cosine t dt minus n dx. N is cosine t, and dx is minus sine t dt. Okay. And if you put all this together, you get cosine squared minus cosine sine plus cosine sine, so you get the integral from t equals 0 to 2 pi cosine squared t dt, and we've done this 1,000 times. This turns out to be pi, and that measures the flux across the unit circle when we're traversing the curve in the counterclockwise direction in this field f equals x minus yi plus xj. All right, so that's the end of 16.2, part 2. And so, yeah, there was one homework problem that had some flux in it. So you might try a few of these. They're very similar to circulation. The only difference is instead of dotting with n, you dot with t.